Find somewhere comfortable. You don't need to sit up straight or arrange yourself carefully. Wherever you are right now, lying down, curled on your side, head heavy against a pillow, that is exactly where you are meant to be. You don't need to follow any of this closely. You don't need to remember it. The words will come and go like water moving over stones, and you can let them pass right through you. Tonight we are going to travel somewhere. Not far. In fact, we are going to travel somewhere you have been every single night of your life, though you have never quite seen it from the outside. We are going to follow the mind as it moves from the bright, busy world of waking into something slower, something older, something the body has known how to do since long before any of us had words for it. The journey from waking to the deepest sleep is one of the most intimate things that happens to a human being, and yet most of us pass through it without ever really noticing. The lights go out, the thoughts thin, and somewhere in the quiet something changes. If you are tired, that is welcome here. If today was heavy, if you are carrying something you have not yet been able to put down, you do not need to put it down before we begin. The journey itself will help with that. The mind knows how to release what it is holding when the conditions are right. We are simply going to help create those conditions together. So settle in. Let the weight of your body rest fully where you are. The world outside is still there, but it is no longer asking anything of you. Not tonight. We are in no hurry at all. There is something quietly extraordinary about the moment just before sleep. Not the moment of sleep itself. That comes later, and we will get there. But the threshold. The in-between. The place where the day is still faintly audible, but already beginning to seem less real, like a conversation heard through a closing door. Almost every culture in human history has had a name to that place. The ancient Greeks called it the realm of Hypnos, the god of sleep, whose kingdom lay in a cave beside the river Lethe, the river of forgetting. To enter sleep was to pass through his domain, to drink, however slightly, from those waters of unknowing. There was something they understood intuitively that science has only recently been able to measure. The transition into sleep is not a simple dimming of consciousness. It is a transformation. A genuine change in the nature of the mind itself. For most of human history, no one really knew what happened inside the sleeping brain. Sleep was understood by its effects, by how you felt in the morning, by the dreams you remembered or didn't, by the strange stories the body told in the night. Aristotle, writing in the 4th century before the Common Era, believed that warm vapors rising from the stomach after digestion caused sleep, like a kind of gentle internal fog. The body, he thought, was simply recovering from the effort of the day. And in a way, he was not entirely wrong. He just didn't have the tools to see how right and how incomplete that picture was. Those tools came later, much later. And when they arrived, they revealed something that no ancient philosopher could have predicted, that the sleeping mind is not resting at all. Not in the way we think of rest. It is working, deeply, intricately, beautifully working. Sorting through the day, repairing the body, consolidating memory, processing emotion, and doing all of this in a series of distinct and carefully orchestrated stages, each one different from the last, each one serving a purpose we are still only beginning to understand. Tonight we are going to travel through those stages, one by one, slowly, and by the time we reach the deepest of them, it is very likely that you will already be there. To understand where sleep takes us, it helps to understand where we begin. And we begin here, awake, in a state that the brain maintains through an almost heroic amount of effort. Wakefulness is not a default, it is an achievement. Deep inside the brain, in a region called the hypothalamus, there is a small cluster of neurons that produces a chemical called orexin. You may also hear it called hypocretin. These neurons are, in a sense, the brain's alarm system. Alongside orexin, the waking brain is bathed in a symphony of other chemicals. Histamine, produced in a region called the tuberomammillary nucleus, keeps arousal steady. Serotonin, norepinephrine. These monoamines hum quietly through the brain during wakefulness, sustaining the sense of being present and alert. And meanwhile, with every hour you remain awake, another chemical is accumulating. A byproduct of neural activity, adenosine builds up slowly in the brain like a tide coming in, gradually inhibiting the very cells that keep you awake. This is what scientists call sleep pressure, the quiet. The electrical activity of the waking brain has its own character. When you are alert and active, thinking hard about something or responding to the world around you, the brain produces what are called beta waves, rapid oscillations cycling somewhere between 12 and 30 times per second. If you could see these waves, they would look like quick, shallow ripples on the surface of a busy harbor. There is energy in them, a kind of urgency, though we do not use that word here. They won't use that word here. They are the electrical signature of a mind that is engaged with the world. We know all of this because of a man named Hans Berger. He was a German psychiatrist working in the early years of the 20th century, and he spent years pursuing what his colleagues considered an eccentric obsession, the idea that the electrical activity of the brain could be measured from outside the skull. In 1924, after more than a decade of careful, painstaking work, he succeeded. He attached electrodes to the scalp of his own son and recorded the first human electroencephalogram, the EEG. The brain, Berger showed, was not electrically silent. It hummed. It pulsed. It sang in frequencies that changed depending on what the person was doing. When we close our eyes and begin to relax, not yet asleep, but no longer quite engaged with the world, something in that electrical signature shifts. The rapid beta waves slow and soften, and a new pattern begins to emerge. Alpha waves. Slower, rounder, cycling at somewhere between 8 and 12 times per second. This is the brain in a state of calm wakefulness, not working hard, not worrying, simply present, resting in itself. Many people who meditate regularly learn to spend extended time in alpha states. There is a quality to them. If today was full and busy and demanding, the shift from beta to alpha can feel like setting down a heavy bag. The shoulders unknit a little. The jaw softens. The breath slows. This is where you might be right now if things are going well. Just here, in the quiet between the day and the dream. The transition from waking to sleep is not a cliff edge. It is a shoreline. The water comes in gradually, and there is a long, shallow place where you are neither fully in nor fully out, where the familiar world and the world of sleep overlap and intermingle in ways that can feel strange and beautiful, and sometimes a little disorienting. This transitional stage, what sleep scientists now call NREM. The alpha waves of relaxed wakefulness give way here to something slower still. Theta waves, cycling at between 4 and 8 times per second. If alpha waves are the electrical signature of calm, theta waves are the signature of deep relaxation, of the mind beginning to untether itself from the present moment. Researchers have found that theta activity is also associated with creativity and intuition. There is something about this loosened, between state that allows the mind to range more freely across its own interior landscape. It is in this stage, or just before it, that many people experience something called a hypnic jerk. The doorway of stage 1 opens into stage 2, and this is where sleep begins to feel more genuinely like sleep. The body temperature drops a little. The heart rate slows. The muscles relax further. And on an EEG recording, something remarkable begins to appear. Among the continuing theta waves, 2 new patterns emerge that are unique to this stage of sleep and have no equivalent anywhere else in the brain's electrical repertoire. The first are called sleep spindles. They are brief, sudden bursts of faster electrical activity, 12 to 15 cycles per second, that appear and disappear in the trace like small, tight spirals. Each one lasts less than 2 seconds. They appear, on average, somewhere between 3 and 8 times per minute in stage 2 sleep, and they are thought to play a crucial role in memory consolidation, in the process by which the experiences of the day are quietly sorted, filed, and integrated into the architecture of long-term memory. The second pattern is called the K complex. It is a single, high-amplitude wave, a sharp downward spike followed by a slower upward curve, that appears spontaneously or in response to external sounds. If someone speaks your name while you are in stage 2 sleep, a K complex will often appear in your EEG trace. The brain has not ignored the sound. It has registered it, processed it, and made a decision. In this case, to continue sleeping. Stage 2. Sleep accounts for roughly 45% of a typical night's total sleep time. It is, in some ways, the workhorse of the sleep cycle. Less glamorous than the deep slow-wave sleep that follows, less vivid than the dream-rich REM sleep that comes later, but essential. Without it, the night's architecture collapses. There is a story worth dwelling on here, about a man named Nathaniel Kleitman. He was a Ukrainian-born physiologist who spent most of his career at the University of Chicago, and he became, in the middle of the 20th century, the most important sleep researcher in the world. He was meticulous, patient, and deeply curious about the nature of rest. In 1938-hour schedule, the Kalligan spent 32 days underground, attempting to determine whether the human body's 24-hour sleep-wake cycle was truly internal, or whether it depended on the cues of the outside. Kleitman's greatest discovery came 15 years later, in 1953, when he and a young graduate student named Eugene Aserinsky attached electrodes to a young boy and observed something that no one had quite seen before. Every 90 minutes or so, the boy's eyes began to move rapidly beneath his closed lids. Not the slow, rolling movements of early sleep, but quick, darting, purposeful-seeming movements. And the brain's electrical activity, at those moments, looked not like sleep at all. It looked like waking. Beyond stage 2, the sleep deepens further, and the brain undergoes a transformation that is among the most profound in all of neurology. The sleep spindles and K complexes fade. In their place, rising like slow tides, come the delta waves. Vast, unhurried oscillations cycling at between half a cycle and 4 cycles per second, high in amplitude, low in frequency. On an EEG, they look like great rolling swells on a deep ocean. Nothing like the quick chatter of the waking brain, nothing like the restless activity of lighter sleep. This is NREM Stage 3. Slow-wave sleep. The deepest and most restorative stage of the entire sleep cycle. And it is, in many ways, the most important. During slow-wave sleep, the brain's neurons begin to synchronize in a way they never do during wakefulness. They fire together, then fall silent together, then fire again. A great coordinated rhythm that sweeps across the cortex in waves. It is as if the brain, which spends its waking hours in a constant, individualistic chatter of separate voices, suddenly becomes a choir, all moving together, all breathing in time. No one is entirely sure why this synchronization happens, or what precise function it serves, but the effects of deep slow-wave sleep are unmistakable. This is when the body repairs itself most actively. It is difficult to wake someone from slow-wave sleep. If you have ever been roused from a very deep sleep, by an alarm or a sudden noise or someone shaking your shoulder, you will know the quality of that emergence. There is a heaviness to it, a confusion, a sense of being pulled from somewhere genuinely distant. Sleep scientists call this sleep inertia, and it can last for several minutes, sometimes longer. The brain, returning from the depths of delta sleep, takes time to re-establish the neural activity patterns of wakefulness. For those few disoriented minutes, you are neither fully. There is a condition, extraordinarily rare, that illuminates just how essential slow-wave sleep is by showing what happens in its absence. It is called fatal familial insomnia, and it is caused by a genetic mutation that progressively destroys a region of the thalamus, the deep brain structure that helps generate and coordinate the slow oscillations of deep sleep. People with this condition begin to lose the ability to sleep, not just to sleep poorly, but to enter the deep restorative stages. First, difficulty sleeping, then worsening insomnia accompanied by anxiety and hallucinations, then a profound inability to sleep at all, accompanied by rapid physical. The memory consolidation that happens during deep sleep is also worth dwelling on. There is something almost moving about it when you think about it slowly. Every experience you had today, every face you saw, every skill you practiced, every emotion you felt is being processed right now as you move through these deep stages of sleep. René Descartes, the 17th century philosopher best remembered for the phrase, "I think, therefore I am," was by all accounts an enthusiastic sleeper. He reportedly spent 10 to 12 hours a day in bed, often not rising until noon. His contemporaries found this remarkable. Descartes himself defended it, suggesting that the sleeping brain was engaged in a kind of active processing, that thoughts were being stored and solidified during sleep in ways that contributed to his waking intellectual life. He was, of course, working entirely from intuition and personal observation, without any of the tools that modern neuroscience would eventually develop. We know now that he was right, and that the slow, vast, ancient waves of deep sleep are at the heart of it. From the depths of slow-wave sleep, the brain begins its ascent. The delta waves thin and quicken. The body stirs slightly. This is REM sleep, and it is, without question, the strangest place in the entire landscape of human consciousness. During REM sleep, the brain is extraordinarily active. Its metabolism increases by as much as 20% compared to wakefulness. The EEG trace looks almost identical to that of an alert, engaged, waking mind. Alpha waves, beta waves, a desynchronized, busy electrical signature. The eyes move rapidly beneath closed lids, darting and tracking as if watching something. The brain is, in a very real sense, switched on, and yet the body is almost completely still. A special mechanism in the brainstem, centered in the pons, sends inhibitory signals to the spinal cord during REM sleep, temporarily paralyzing the major muscle groups. The dreams of REM sleep are different from the fragmentary images of lighter sleep. They are vivid, narrative, emotionally charged. They have characters and settings and plots that shift and dissolve and reconstitute. They feel real, in the way that only dreams can feel real, completely convincing from the inside, however strange they may seem from the outside. And they are doing something. Researchers believe that REM sleep plays a crucial role in emotional regulation, that the brain uses the dream state to process difficult or emotionally significant experiences, to integrate them, to strip away some of their raw emotional charge while preserving the informational content. The discovery of REM sleep by Kleitman and Asarinsky in 1953 was one of the most significant moments in the history of neuroscience. It demolished the prevailing assumption that the sleeping brain was largely inactive, a quiet, resting organ simply waiting for morning. Instead, it revealed that sleep was structured, cyclical, and profoundly active. The brain was not merely surviving the night. It was working through it. Each sleep cycle lasts approximately 90 minutes, and over the course of a full night's sleep, a person typically passes through 4 or 5 of these cycles. But the composition of the cycles changes as the night progresses. In the early cycles, slow-wave sleep dominates. The body is doing its most intensive physical repair work in those first few hours. This is why the timing of sleep matters so much. If you cut your sleep short by an hour or two, you are disproportionately losing REM sleep. the emotionally restorative, cognitively enriching, dreaming sleep that accumulates in the later hours of the night. The body's physical repair work, happening in those early cycles of deep, slow-wave sleep, is largely preserved. But the emotional processing, the memory integration, the creativity and connection that REM sleep provides, these are the first casualties of a shortened night. There is a condition, distinct from sleepwalking and often misunderstood, called REM sleep behavior disorder. In typical REM sleep, remember, the body is paralyzed. The muscles are held still by that inhibitory signal from the brainstem. But in REM sleep behavior disorder, that signal fails. The body is free to move, and so people with this condition act out their dreams, sometimes gently, sometimes vigorously, sometimes in ways that can be dangerous to themselves or a sleeping partner. They shout, they gesture, they climb out of bed and move through their dream. They are asleep, deeply and genuinely asleep, but their body. Sleepwalking, by contrast, is a different phenomenon entirely. It occurs not during REM sleep, but during slow-wave sleep, in the deep first half of the night. Sleepwalkers are not acting out dreams. They are moving through the world in a state of deep NREM sleep, their behavior apparently purposeful, but their consciousness genuinely absent. They can navigate familiar spaces, open doors, even speak, without any awareness of what they are doing. When they wake, they remember nothing. The night deepens now. We have traveled a long way, from the bright electrical chatter of the waking brain, through the soft alpha of relaxed eyes closed, through the theta waves of the threshold and the sleep spindles of stage 2, down into the vast, slow delta of the deepest sleep, and back up again into the paradoxical, dreaming activity of REM. There is something quietly wonderful in recent research about all of this, something that feels worth carrying gently into sleep. In 2022, researchers at Massachusetts General Hospital and Beth Israel Deaconess Medical Center published a study drawing on data from more than 8,000 adults. They found that the patterns of brainwave activity recorded during a single night of sleep could predict, with meaningful accuracy, the likelihood of a range of health outcomes over the following 10 years. Sleep, the study suggested, is a kind of window into the overall health of the body and brain. The quality of those waves, and then there is the work being done on what researchers call brainwave entrainment. The idea that the brain's electrical activity can be gently guided towards certain frequencies by external rhythmic stimuli. Sound, most commonly. A tone that pulses at a certain rate, or two slightly different tones played separately into each ear, creating what is called a binaural beat, a phantom rhythm that the brain perceives and, in many cases, begins to follow. Studies have found that exposure to delta frequency rhythms, those slow, deep pulses at between half a cycle and 4 cycles per second, can increase the proportion of slow-wave sleep in a night. There is also research published in 2025 exploring something called personalized sound sequences, audio derived not from a standard frequency, but from the individual's own slow-wave brain activity, translated into sound and played back to them during sleep. What, exactly, is the mechanism by which sleep pressure is tracked? The adenosine accumulation is part of the answer, but the precise neural circuitry underlying the sleep homeostat, the system that knows how much sleep you need underlying the sleep homeostat, the system that knows how much sleep you need and insists on it, is not yet fully mapped. And there is the deeper question still, the one that philosophers and neuroscientists have wrestled with it. What is consciousness, really? What is the thing that goes away when you fall asleep and comes back when you wake? A 2025 paper in PLOS Biology offered a fascinating, if partial, answer. The brain falls out of the particular kind of organized complexity that makes experience possible. The hard problem of consciousness, the question of how any physical process gives rise to the felt quality of experience, to the sense of there being something it is like to be you, lying here, listening to these words, remains unanswered. Perhaps it always will. Somewhere in the ancient world, in temples dedicated to Asclepius, the Greek god of healing, people would come to sleep. They would purify themselves, make offerings, and then lie down in a special hall called the Enquemiterion, the sleeping place. They believed that healing would come to them in dreams, that the god would visit them in the night and speak to them, that the answers to their deepest questions would arrive not in the busy hours of waking, but in the quiet, receptive hours of sleep. We smile at this now, perhaps. We have our science, our EEGs, our polysomnography, our neurotransmitters and brainwave frequencies. But there is something in that ancient practice that understood something true. The night is long and patient. The cycles continue their unhurried turning. Delta waves rise and fall. Dreams unfold and dissolve. Memories are quietly filed. Wounds, in the smallest and deepest sense, begin to heal. All of this is happening right now in the sleeping bodies of countless people, in darkened rooms across the world. All of this is beginning to happen in you. The waking mind, with all its beta wave urgency, its orexin and its histamine and its constant forward motion, is releasing its grip. The adenosine has done its work. The VLPO neurons have fired their inhibitory signals. The arousal centers are quieting. The tide has come in. Whatever you are carrying today, whatever the weight of it, whatever its shape, you don't need to put it down deliberately. Sleep will do that for you. Gently and without asking permission, the night will take it and hold it somewhere at a distance, and in the morning it may look different. It often does. The alpha waves have softened. The theta waves are drifting now, slow and wide. Somewhere ahead, the delta is waiting, vast and still and ancient, the deepest quiet the mind can know. You are already on your way. And so we leave it here, at the edge of the deep. Behind you, the day is already growing distant, already losing its sharp edges, already becoming the kind of thing that can wait until morning. The body knows where it is going. It has always known. Sleep well. Hansberger's path to that discovery was not straightforward. For years, colleagues dismissed his work as wishful thinking, as the obsession of a man who had perhaps strayed too far from respectable medicine. He published his findings in 1929, and the initial response from the scientific community was largely skeptical. It took the intervention of Edgar Douglas Adrian, a British physiologist who would later win the Nobel Prize, to independently verify and publicly champion Berger's results. Only then did the world begin to take the idea seriously. There is another dimension to the waking brain worth resting with for a moment. The default mode network, a set of interconnected regions that becomes active when the mind is not focused on any particular external task, is one of the most studied and, in many ways, most mysterious systems in neuroscience. When you are not thinking about anything specific, when your attention drifts inward, when you are daydreaming or remembering or imagining, the default mode network is quietly humming. It is the neural substrate of the wandering mind, and there is something interesting in the fact that this network, which dominates so much of our inner life during wakefulness, shows dramatically reduced activity as we move into deep sleep. The experience of the threshold is not the same for everyone, and this is worth acknowledging gently. For some people, the crossing into sleep is smooth and almost imperceptible. The thoughts simply thin, the body grows heavy, and the next thing they know, it is morning. For others, the threshold is a place of difficulty. The thoughts, rather than dissolving, sharpen. The body, rather than releasing, tightens. They are something the brain moves toward when the conditions allow, and sometimes the most useful thing is simply to stop trying to hurry them along. There is a researcher named Sonia Ancoli Israel, a sleep scientist who spent decades studying sleep across the lifespan, who made an observation that has stayed with many of her colleagues. She noted that older adults who often complain of difficulty falling asleep are not necessarily sleeping less than they need. What changes with age, she found, is not so much the need for sleep as the architecture of it, the proportions of the different stages, the ease of the transitions, the depth of the slow wave periods. The brain's ability to generate those great delta waves diminishes with age, and the sleep that results is often lighter, more fragmented, more easily disturbed. Sleep spindles, Those brief bursts of faster activity in stage 2 are also worth dwelling on a little longer. They are generated by a structure called the thalamic reticular nucleus, a thin shell of neurons that wraps around the thalamus like a net and plays a central role in gating the flow of sensory information to the cortex. During sleep, this structure is thought to act as a kind of sensory filter, suppressing incoming signals that might otherwise wake the sleeper. A door closing in another room, a car passing outside, the distant sound of a voice. These reach the thalamus, but are blocked or dampened by the reticular nucleus and its spindle-generating activity. The sleeping brain is not passive. The glymphatic system deserves a little more time because it is one of the more recent and genuinely remarkable discoveries in sleep science. For most of the 20th century, the brain was believed to lack a lymphatic system, the network that the rest of the body uses to clear waste products and regulate immune function. The brain, enclosed in its bony case, seemed to manage waste by other means, or not to manage it particularly well at all. But during sleep, particularly during deep, slow-wave sleep, the brain's cells appear to shrink by as much as 60%, opening up the spaces between them and allowing the glymphatic flow to increase dramatically. The brain, in its deepest sleep, is literally washing itself clean. The implications of this discovery are still being explored, but one of the most significant concerns a protein called beta-amyloid. Beta-amyloid is one of the proteins that accumulates in the brains of people with Alzheimer's disease, forming the plaques that are associated with cognitive decline. And it is one of the waste products that the glymphatic system clears during sleep. Studies have shown that even a single night of sleep deprivation leads to a measurable increase in beta-amyloid accumulation in the human brain. Chronic sleep deprivation over months and years may therefore contribute to the conditions that make neurodegenerative disease more likely. This is not a reason for anxiety. Again, the research here is there is a quality to slow-wave sleep that is worth trying to imagine, even if imagination cannot quite reach it. In that state, the brain is doing something that has no parallel in waking life, producing those vast, synchronized oscillations that sweep across the cortex in slow waves. Neurons firing in unison and then falling silent together over and over in a rhythm that is at once deeply orderly and profoundly unlike anything the waking brain produces. Some researchers have described it as the brain's equivalent of a reboot, a periodic clearing of the system, a resetting of the neural baseline. Others have compared it to the tides. The question of why we dream is one that has occupied human beings for as long as there have been human beings to be occupied by it. In ancient Mesopotamia, dreams were understood as messages from the gods or as portents of things to come. The Epic of Gilgamesh, one of the oldest written stories in human history, contains detailed accounts of prophetic dreams and their interpretations. In ancient Egypt, there were specialists called dream interpreters who served in temples and courts, whose job was to decode the symbolic language of the sleeping mind. Freud, at the turn of the 20th century, proposed one of the most compelling theories of dreaming in contemporary sleep science is the threat simulation theory, proposed by the Finnish researcher Antti Revoncio. Revoncio suggested that the primary function of dreaming is to simulate threatening situations, to provide the brain with a kind of rehearsal space for dealing with danger. In dreams, we run, we hide, we confront, we navigate, and through this rehearsal, the brain maintains and sharpens the emotional and behavioral responses that will be needed in real threatening situations. It is a theory that fits with the observation that many dreams, particularly in children and in people who have recently experienced difficult events, have a strongly threat. A complementary theory, developed by Matthew Walker and others, focuses more specifically on the role of REM sleep in emotional memory processing. Walker and his colleagues have shown that the neurochemical environment of REM sleep is unique in one very specific way: the brain's levels of norepinephrine, the chemical associated with stress and anxiety, fall to their lowest point of the 24-hour cycle during REM sleep. The brain is dreaming in a bath of reduced stress chemistry. This, Walker suggests, allows the brain to reprocess emotionally significant memories, to replay them, to integrate them, to extract their meaning, without the raw emotional charge that would accompany that processing during wakefulness. There is a study from the early 1990s that has become something of a landmark in dream research. Researchers at Harvard, led by Robert Stickgold and J. Allen Hodson, asked participants to spend several hours learning a new skill, navigating a complex virtual maze. Those who were allowed to sleep afterward and who reported dreaming about the maze showed dramatically better performance on the task the following day compared to those who had not dreamed about it. There is also something worth noting about the content of dreams that many people find quietly reassuring. Studies of dream content, large-scale analyses of dream reports collected over many years, consistently find that the emotional tone of dreams is predominantly negative. More anxiety, more threat, more loss than joy or pleasure. This can sound disheartening, but the interpretation offered by many researchers is the opposite. If the function of REM sleep is emotional regulation, if the dreaming brain is specifically seeking out and processing the difficult, the unresolved, the emotionally charged, then a predominantly difficult dream landscape is exactly what you would expect. The brain is... There is one more thing worth letting drift through your awareness as the night deepens. The concept of sleep architecture, the precise pattern of stages and cycles that makes up a full night's sleep, is not fixed. It varies from person to person, from night to night, across the lifespan, and in response to the events of the day. A night in which you experience something emotionally significant will typically produce more REM sleep than usual, particularly in the later cycles. A night following intense physical exercise will often produce more slow-wave sleep as the body takes the opportunity to do additional repair work. The brain and body are not following a rigid program. The researchers who study sleep in non-human animals have found that the basic structure of sleep, the alternation between NREM and REM states, the presence of slow oscillations and sleep spindles, is conserved across a remarkably wide range of species. And there is the moon, somewhere above the clouds or the rooftops or the ceiling of wherever you are. For most of human history, before the electric light changed everything, the night sky was the primary regulator of human sleep. People slept in two phases, separated by an hour or so of quiet wakefulness in the middle of the night, a pattern that historians and sleep researchers have found evidence for across many pre-industrial cultures. The historian Roger Eckersh spent decades documenting references to first sleep and second sleep in historical texts, diaries, and court records, and found them scattered across centuries and continents. In that middle hour, people would, but somewhere in the biology of the body, the old pattern may still be present, which is why waking at 2 or 3 in the morning and lying quietly for a while is not necessarily a sign that something has gone wrong. It may simply be the body remembering something older than electricity,